Okay, let me ask you a question. What if your manufacturing process could get smarter every single day? I mean, what if your production line could constantly experiment, optimize, and improve itself, all without ever having to stop production? Now, I know that sounds like science fiction, but it's not. It's a really powerful statistical method from all the way back in 1957 called evolutionary operations, or EVOP, and you're about to see why it's more relevant now than ever. So here's how we're going to break this all down. First, we'll look at the core framework, what EVOP actually is. Then, we'll make the business case for why you'd even want to do this. After that, we'll get into the nuts and bolts of how to execute it, walk through a fantastic real-world case study involving chocolate, and then wrap up with some advanced considerations you'll want to keep in mind. All right, let's dive right in with the fundamentals. This method has been around for decades, which is wild because the core idea feels so incredibly modern. So, at its heart, what exactly is evolutionary operations? At its core, EVOP is a really disciplined way to inject learning directly into your live operations. You know how we usually treat a process like it's a static black box? You set it, you run it, you don't mess with it. EVOP turns that idea on its head and says, let's turn that black box into a living laboratory. The key here is that it relies on systematic, small changes. We're not talking about disruptive overhauls here. Think of it more like making tiny controlled adjustments that are so safe they don't risk your output, but they generate absolutely invaluable data. The philosophy behind EVOC is just brilliantly simple, and it's actually borrowed directly from nature. It runs on two fundamental engines. First, you introduce intentional, planned variation into your process. Then, you practice selection. You look at the data, identify what worked best, and use that information to decide your next move. It's this beautiful, continuous cycle of creating options and choosing the best one, constantly pushing your process to evolve toward its best possible state. So now that we've got the what, let's really dig into the why. What's the big strategic advantage here? Why would you shift from that classic, if it ain't broke, don't fix it mentality to one of constant, controlled tinkering? This chart just perfectly illustrates the paradigm shift. A traditional static operation, it runs on standard work. The whole goal is consistency, right? Any deviation is a risk you want to stamp out immediately. But with EVOP, that thinking is totally flipped. Deviations aren't risks, they're planned, they're controlled, and they are treated as a critical source of information. And what this does is it fundamentally breaks down that wall between production and R&D, merging them into one single powerful continuous improvement engine. Now, it's really important to get this. EVOP is not a silver bullet for every single problem. It's more like a precision tool for very specific, very common challenges. It really shines when you have just a few key variables to play with. Think temperature and pressure. It's perfect for those processes that kind of drift over time. And it's designed to be simple, avoiding super complex math while making sure you don't create a mountain of scrap just to learn something new. All right, so we've covered the what and the why. Now let's get into the mechanics. How does this build into a practical, repeatable framework that you could actually go out and use? This is the operational playbook for EVOP. You start by defining your goal. What are you actually trying to make better? Then you pick your levers, those 2 or 3 variables you can control. You plan some small, safe changes, and you run a set of experiments. But the real magic is in those last steps. You analyze the results, you find this single worst outcome, and then you strategically replace it with a new experiment that's a reflection of that worst point. This systematically walks your process away from poor performance and toward those optimal settings. Now, you're going to hear this term simplex a lot, and I know it sounds technical and intimidating. Don't let it fool you. It's just a simple way to visualize your experiment. So if you're testing 2 variables, let's say temperature and pressure, your different experimental points form a triangle. That triangle, that's your simplex. That's all it is. It's just the geometric map of what you're currently testing. Okay, theory is great, but let's make this real. We're going to walk through a case study from the ABC Chocolate Company and see how they use this exact process to solve a pretty serious production problem. So this was the problem they were staring down, a rejection rate of over 21%. I mean, that is a staggering amount of waste. It was killing their efficiency, it was messing up their schedules, and it was hurting customer satisfaction. The pressure was on to find a fix, and fast. So they followed the playbook. The team defined their goal. Get that scrap rate way down. They identified 2 key variables they could easily control: the air pressure in the machine and the speed of the conveyor belt. They set their starting point, and then they plan small, incremental changes to test around it. And right here, you can see the evolution happening in real time. Their first set of runs showed that run 1 was the worst performer. It had the highest rejection rate, so they just eliminated it. And they performed run 4, which was a calculated reflection of run 1. Now they had a new set of runs, 2, 3, and 4. And in that group, run 3 was the worst. So what did they do? They did it again. They replaced run 3 with its reflection, run 5. See how each cycle just methodically pushes the process toward a better outcome? It's brilliant. And this is the simple but incredibly powerful engine that drives that evolution. The settings for the new run aren't just a random guess. They're calculated by taking the sum of the 2 good points and then subtracting the worst point. This little mathematical step ensures that every new experiment is a deliberate move away from the least desirable corner of your experimental space, your simplex. Okay, to wrap things up, we need to talk about a critical detail and how these experiments are designed. The method we just saw in the chocolate example is super effective, but it's not the only way to design an EVOP experiment. Let's quickly look at the difference between simplex and factorial designs. In fact, someone who read the original source material, a sharp observer named Alejandro, pointed this out. He noted that while our chocolate example uses a simplex method, traditional EVOP, as George Box first imagined it, often used something called full factorial designs. And he's right, it's a really important distinction for anyone looking to do this properly. So here's the key difference. Think of it like the tortoise and the hare. The simplex design, the one from our chocolate story, that's the hare. It's incredibly efficient, designed to find the path of improvement as quickly as possible with the fewest number of runs. The more traditional factorial design, on the other hand, is the tortoise. It's a bit slower, but it's way more comprehensive. It tests all the combinations of your variables at high and low settings, which gives you a much more complete picture of your process. So your choice really just depends on what you need most, speed to an insight or a complete understanding of your process. But look, at the end of the day, no matter which design you use, the big takeaway is exactly the same. EVOP is this powerful management philosophy that embeds the process of discovery directly into your day-to-day work. It transforms your production line from just a cost center that makes things into a strategic asset that generates both product and knowledge. So I'll leave you with a challenge. Take a look at your own operations, your own standard work. And don't just ask where you can cut costs. Ask yourself, where is the untapped potential for evolution? Where can we turn our production into our own private R&D lab?